Welcome back to differential equations. In this video, we're going to be going through a review of integrals. If a differential equation is an equation that relates a function to its derivatives, well, to get rid of a derivative in order to solve an equation is likely going to involve an integral. Although, to be fair, spoilers, we're going to find a lot of tools that are going to let us sidestep actually performing an integral. They don't always work, so having integrals in our back pocket is definitely going to be something worthwhile. Let me get my head out of the way and let's go through some of the basic ideas. The first thing I want to mention is the difference between an indefinite integral and a definite integral. The notation for the two is similar, but the distinction between how we evaluate them and the kinds of results that we should expect is going to be very key. Again, this should be something you're familiar with from a previous calculus course, but it's worth reviewing. So if, for example, I wanted to take the integral of something relatively straightforward, how about the integral of dt over t? Set up like this, it is an indefinite integral. And in order to evaluate the indefinite integral, we need to find the antiderivative. We need to think back to our list of functions and figure out which one has a derivative that looks like 1 over t. The answer in this case is the natural log. So the natural log of t. And a lot of times, especially when we're talking about time, negative values of t aren't going to make any sense. But to be technically correct, when we have an integral that gives us a natural log, it should be the natural log of the absolute value of the stuff inside. And if we took the derivative of the natural log of the absolute value of t, we would in fact get 1 over t, which is exactly what we wanted. But that's not the only thing that would give us that derivative. Because if I add any arbitrary constant to the natural log of t, the derivative of an arbitrary constant is 0. That doesn't change anything. So the derivative is still 1 over t. Right. When we take an indefinite integral, we get a family of functions as our result. A family of functions is a setup like this that involves an arbitrary constant. And it's often going to be important to look at indefinite integrals. And as we continue our study of differential equations, thinking about where, why, and how that arbitrary constant comes up is going to be one of the big keys. Compare that to a definite integral. Say the integral from 1 to 5 of dt over t. Well, the setup here starts out much the same. We look at dt over t and we ask ourselves, what is an antiderivative? What kind of thing do you take the derivative of so that it spits out dt over t? And we realize that the natural log of the absolute value of t is just the thing. And then we evaluate that antiderivative at the endpoints. So we end up with the natural log of 5 minus the natural log of 1. You may recall that the natural log of 1 is just 0, and so we get the numerical solution here natural log of 5. If you really cared, you could grab out your calculator. My calculator is quite happy to tell me that the natural log of 5 is something in the ballpark of 1.609. But when you take a definite integral, the result is a numerical value. Again, that should be something you're very familiar with. That's an idea that shows up very early in calculus and continues throughout your study of calculus. But it is going to be important here. So if it's been a while since you've taken calculus, something to think about. When it comes to actually evaluating integrals, we have a couple of powerful tools. Of course, being able to identify an antiderivative is important. Being able to look at something and say, oh, this is a thing who shows up when I take the derivative of natural log, or when I take the derivative of tangent, or whichever function it might be. But that's certainly not the only thing that we have at our disposal. There are a number of tools that you can use for calculating integrals, for finding antiderivatives. I want to look at 3 in particular that will be useful to us in this course to one degree or another. Or at least that's what I'll try if technology will cooperate with me. All right. The first tool is the method of use substitution. So for example, if I'm looking to take the integral of 2x plus 3 over the square root of x squared plus 3x plus 5 dx, I might notice that I've got a real mess on my hands. But if I let u equal x squared plus 3x plus 5, and then I differentiate, the derivative here is in fact 2x plus 3 dx. And so I've got my u down here underneath the square root. I've got my du hanging out up here in the rest of it, and I can rewrite this integral as du over the square root of u. Using properties of exponents, I can rewrite this further still as u to the negative 1/2 power times du, which makes it a little bit more obvious that we're using the power rule here. And we're going to end up with, well, negative 1/2 plus 1 is positive 1/2. 1 divided by positive 1/2 is 2 times u to the 1/2 power plus our arbitrary constant. Then take the value we have for u, plug it back into this expression, and we're going to get 2 times the square root of x squared plus 3x plus 5 plus our arbitrary constant, and there is the solution to this integral. Moving onward, up next I have integration by parts. Integration by parts formula tells us that the integral of u dv is equal to uv minus the integral of v du. This comes from looking at the product u times v, differentiating using the product rule, integrating both sides of the resulting equation, and then rearranging it. And if we carefully select so that the part we call u is something that gets simpler when we differentiate, And the part we call dv is something that gets simpler, or at least no more complicated, when we integrate. Then we can figure out how to find the integral of something we might not know how to integrate otherwise. The classic example for integration by parts is the integral of x times e to the x dx. There is no elementary way of doing this unless you just happen to know what the integral comes out to. But if we let u equal x and we let dv equal the rest of it, e to the x dx, then we can figure out what du is by differentiating. And here's where this was a useful choice. The derivative of x is just dx. And with our integral here, the integral of e to the x is just e to the x. It doesn't get any more complicated. We could have tried to set this up the other way. Let u equal e to the x and let dv equal x dx. If we had done that, we would end up with a much more complicated thing at the end, which is a sign that we did things backwards. All right, but now that we have that, it's just a matter of following the formula. U is x, v is e to the x, v is still e to the x, du is dx, and the integral of e to the x dx is just e to the x. And then, of course, when we take an integral, there's always the possibility of an arbitrary constant of integration. So x times e to the x minus e to the x plus our arbitrary constant of integration. Technically, in this one, that plus c should be grouped in. So, e to the x plus c all in parentheses. But then we get into the we don't care kinds of technicalities, because you can distribute that subtraction through. So we get minus e to the x minus our arbitrary constant. But if the constant is arbitrary, it doesn't matter if you're adding it or subtracting it. Right? Just choose a different arbitrary constant. I wanted this to come out as minus 3.25. Well, instead of choosing c equals 3.25, choose c equals negative 3.25, and you get the same function out. So we can be very fast and loose with how we deal with our arbitrary constants. Sometimes that makes things a little bit more messy than it needs to, but getting used to that is one of the key things that I want you to work on during this course. As you move onward, especially if you're going beyond mathematics to the applied mathematical sciences, physics, engineering, finance, you're going to find that caring about the details is something that they just don't do in those fields. Constants arbitrarily change shape. You use the same symbol to mean two different arbitrary constants because it doesn't really matter in the end anyway, and it goes without comment. If you aren't used to that, it is incredibly difficult. So it's something specifically I want you to work on as you're looking at integrals in this course. Pay attention to when we care about the arbitrary constant, and pay attention to when we can get away with things like, well, minus c and plus c is effectively the same, or c and 2 times c is effectively the same. It's something we use quite a bit, and it's something that's worth spending some time thinking about. All right, one last trick of integrals. Again, there's a ton of different techniques you've learned for integration in the past. The last one that I want to think about is the tool of partial fraction decomposition, which is always a lot of fun. That is incredibly sarcastic if you didn't catch it. But partial fraction decomposition allows us to look at something like the integral of dx over x squared plus 5x plus 6 and find a way to approach this sanely. Although I should mention that for this particular problem, there's other ways that we could solve it other than using partial fraction decomposition, but we're going to use partial fractions actually for tools that aren't directly integration. Later on in this course, we're going to see something called the Laplace transform, which is an idea related to the derivative and integral, but not the same as the derivative and the integral. And partial fractions are going to be useful there as well. So this is a chance to practice partial fractions more so than it is necessarily the best way to solve this particular integral. But the idea of partial fractions is to take the fraction that we're looking at, in this case it's 1 over x squared plus 5x plus 6, and recognize that the denominator of this fraction will factor. And specifically, it will factor into x plus 2 times x plus 3. The idea of partial fractions is the claim that there has to be a way to rewrite this fraction as some constant a over x plus 2 plus some other constant b over x plus 3. And if we can figure out what the values of a and b are, then we can perform the integral, because we could split this up. So we can turn this into the integral of, well, a times the integral of dx over x plus 2 plus b times the integral of dx over x plus 3. All we have to do is figure out what a is and what b is. And we do that here by method of first finding a common denominator, clearing out the fractions and rewriting this as a polynomial, and then using a property from linear algebra that says the two polynomials are equal if and only if they have equal coefficients. All right, so I multiply both sides of the equation by the denominator, x plus 2 times x plus 3. Well, 1 over x plus 2 times x plus 3 multiplied by x plus 2 and by x plus 3, those cancel each other out, and we're left with 1. If I take a over x plus 2, and I multiply by x plus 2, and I multiply by x plus 3, the x plus 2's cancel each other out, and I'm left with a times x plus 3. Then if I take b over x plus 3 and I multiply by x plus 2 and by x plus 3, the x plus 3's cancel each other out, and I'm left with b times x plus 2. All right, so rearranging things here a little bit. We have a times x, we have 3 times a, we have b times x, we have 2 times b. And if I get all of my x terms together, on the left-hand side, there's no x showing up anywhere, so I get that x 0 on the left-hand side. And on the right-hand side, the coefficients on x are a plus b. Then if I get my constant terms together, on the left-hand side, the constant term is 1. On the right-hand side, the constant terms are 3a plus 2b. This is a system of two equations in two unknowns. And if we can find the solution to this system, then we know what a and b are. We can plug it back into the original equation, or the original integral, and solve the integral. All right. I'd like you to take the time to finish this one off. Solve this system, plug it back in, evaluate the integrals, see what you can do with that, and I'll see you in the next video.